All right, we're going to look at a little thin film interference problem. This says find the two thinnest films of oil on water that will appear red when viewed from above. So what we want to think about is in these thin film interference problems, you have light coming down on the surface, and some of that light actually bounces off the very top of the film. So there's like ray number one, and some of this light will actually transmit through the film and then bounce off of the bottom surface and comes back. And so that's why you have an interference effect from from light waves coming down. You have light bouncing off the front and light bouncing off the back of the film. And so what we want to do is, first let's decide if we want to have constructive or destructive interference. Well, this says that it will appear red. So that means it's going to give back red light. Okay, so one part of our process is we decide that we want constructive interference. And that's given by the idea that it will actually look that way. Now, if you wanted destructive, you'd see words like, oh, it will cut out red reflections or something like that. But we want constructive. Now, the usual conditions, so usually for constructive, the usual condition is delta path, the path difference, equals n lambda, equals an integer multiple of wavelengths. Now what we're going to have to do here, though, is decide if that is still going to give us constructive interference. And so something we have to look at are these boundaries in the film. So if you look at the top surface, we're going from air, which has an index of 1.00 out here in the air, to oil. Well, that is what's called a hard boundary because you're going up in index. And what's going to happen is at hard boundaries, peaks become valleys. Okay, you get a what's called a 180-degree phase shift that changes all the peaks in this wave into valleys upon reflection. The second boundary is what's called a soft boundary. You're going from a high index material to a low index material. So that's a soft boundary, and what happens there is the peaks remain peaks. Okay, so what's happening here is since the peaks kind of become valleys here, and I'm actually going to write that down, peaks become valleys, right? And here the peaks remain peaks. What happens is this top wave, the wave that bounces off the top surface, the peaks become valleys. And so what's happened is we've messed up what should be the usual condition for constructive. So because of the boundaries here, because you've messed with one of the waves, you're going to have to reverse this condition. So we're going to say here, delta path equals n plus 1/2 lambda is constructive because of the boundaries. The upshot is, if these were both hard boundaries or both soft, then this would still be constructive. But because you've messed with one of the waves, which would be with having one boundary be hard and the other soft, and it turns out it doesn't matter which, then you'll have to reverse the usual conditions. Okay, so now we're about ready to go. Let's look. There's a couple more things we have to do yet, though. One of them is looking at the path difference. Now, if we say that we're just looking from above, I know I've drawn these at a bit of an angle, but the idea is to think about the rays just kind of coming straight down and straight back up. So what's happened here is ray number 2 has had to go through the film and back up through the film. So it's had to traverse the thickness of the film twice. So what that means is your delta path is actually 2 times the thickness of the film, right? Now over on the other side, we have this n plus 1/2. Now, something to watch out for here is this wavelength always needs to be the wavelength that's actually in the film, okay? Because the extra path that's being followed by this second ray, the wave is going through peaks and valleys, and what we're trying to do is figure out how those peaks and valleys line back up with the original wave when they come out. So what we really need to pay attention to then is the wavelength when we're actually in the oil, okay? So we're going to do a little side project on that just to get the wavelength within the film. So by the way, in all these problems, when you're looking for thin film interference phenomena, you really are interested in the wavelength within the film, okay? And so a quick little side project that we can do to get that is you can say, well, this product, n1 lambda 1, it's actually a constant then, equals n2 lambda 2. And so what we can do is plug in the known values from the air and then the known values for the oil. So what you can do is say, well, in the air, we have the index is 1, and the wavelength was 650. And in the oil, which has an index of 1.6, we're looking for the new wavelength, the lambda in the oil. And so what we need to do then is divide 650 by 1.6, and that will give you 406.25. Right? And so now just to finish the problem off, we're supposed to find the two thinnest films. So that's going to occur for n equals 0 and n equal 1. So let's just finish this problem off. For n equals 0, we get half of 406.25, but then we're going to have to divide it by 2 again. So that's going to be 406.25 divided by 4. Which is going to give you a 101.6 nanometer film. That's the very thinnest film. And then the next one would be for n equals 1. And so then we're just going to put in 3 halves times 406.25, but then we're going to have to divide by 2 again. So that's going to be 3/4 of 406.25. So 0.75 times 406.25. And that's going to give us 304.7. So those are the two thinnest films that would actually appear red. It would give you back light that is of wavelength 650 nanometers in the air.